All right, welcome to the second and final installment of video PowerPoint presentations for periodic table of the elements. And as you can see here on the very first slide, there is something very similar to the model of the periodic table that I have in the classroom. I've always wanted one of these. Of course, the one I have is not as complete as this one. Maybe someday I'll work on it, but it has all of the examples of the real elements inside each of the spots that each element takes up on the periodic table. So that's just a really neat collection, I think, as a scientist. So we're going to be talking about all of the families or groups of elements today on the periodic table. We're going to start with the alkali metals. So the alkali metals are the first column or group or family, and they pertain to lithium, sodium, potassium, rubidium, cesium, and a unique element. Well, they're all unique, of course, but francium. Francium is so unique, it has never actually been seen. It's a very short-lived radioactive element discovered by Marie Curie and her husband, and formed when other radioactive elements break down. It's a very short half-life, like 0.006 seconds or something like that. So once it's there, bloop, it's gone. That's how fast the radiation leaves and changes it to another element. So as you're copying down the information, you're filling in the little table on the bottom right there. I'm going to tell you a little bit of information about some of these. So now, I suggest later that you go look up cesium explosion or rubidium explosion, because there's some really neat videos on YouTube where these guys and girls, they take little tiny amounts of cesium, like the amount that would fit in your pencil or pen, that volume, and they throw it into a bathtub full of water, and it just blows up like a hand grenade. It's just incredible. All of these alkali metals react violently with water. Even sodium, which is a very soft metal, so soft you can cut it with a butter knife. It will pop and fizz and sparkle, and a big enough piece will explode if you threw it in a lake or something like that. There's lots of videos of this on YouTube, so if you're interested, it's pretty cool. But I mean, sodium is just, people think, oh, reduce your sodium in your meal. We're not eating the metal. It's chemically bonded to something else, and we're going to talk more about that later. When you chemically bond things, their properties change. So these are the alkali metals. Many different uses. Some of you know because you did projects on some of these. Oh yeah, lots of little dad jokes here. Group 2, alkaline earth metals. Okay, this is the second column, and this has beryllium and magnesium, calcium, strontium, barium, and radium. Now radium, that's actually not radium. That is actually a mixture of radium bromide and zinc sulfide used in glow-in-the-dark watch faces years ago. And while you're copying down this information about the alkaline earth metals, I'm going to tell you a little story about that. Okay, so this is a play was actually made about the women who worked in the watch factories, and they would have to paint this radioactive material onto the watch faces as numbers and the hands of the watch. So when you look at your watch at night, it glows and gives off light. But this is not the kind of light that's like in my watch, the watch that I showed you with electrons doing quantum leaps. This is radioactive decay. So alpha particles and beta particles and gamma rays were coming off of this material and getting all the workers sick. See, they had to use very fine tip paintbrushes, and the only way to get the paintbrush to be fine enough is that they had to put it in their mouth and lick it, like you maybe if you ever threaded a needle, you put it in your mouth to make it thinner and it fits through the hole. They were ingesting it. Their bodies actually glowed. They were glowing after a number of years of working in these factories. And in the end, even though many of them died, they fought the industry, and a lot of changes for safety were made because of their sacrifice. A lot of changes in the way that industry handles its employees. Magnesium is pretty cool. You can take little tiny shavings of magnesium and set it on fire. A lot of these elements actually are flammable metals. Better read them quick. I'm going to move the slide. Okay, so I'm not going to spend a lot of time on this slide number 6, but in your notes, you can see that all these questions are there. Now, on a normal year, because of COVID, we need to dispense with working in groups to answer these questions, okay? Because that's just working too close together and too much talking going on in a close proximity, and that's just not going to happen. So your job is to do this on your own, and there's going to be one more of these sets of questions in these notes. Okay, so it's a lot of questions, but they're not that challenging. Okay, like how does lithium number 3 compare or contrast with cesium? So you would just look at those and see the differences. It's really fast. Okay, so now we're going to take the entire center section, which is called the transition metals, because we're transitioning from the left side to the right side. And we're going to talk about them in one chunk because actually they have a lot of commonalities. So gold is an example. Many transition metals, but not all, like gold, are silver colored. And of course, gold is the exception. Most of them are silver. Like this, that is a artificial hip joint through an X-ray. And it's made out of titanium. That's what it looks like in reality. Silver looking, right? And the reason that you can use titanium in a human body is because it's not very reactive. The reactivity ranges from metal to metal, but they're definitely less reactive than the alkaline earth metals. And some of them are more reactive than others. If you were to make somebody an artificial hip bone and socket, or the ball part that goes in the socket, out of iron, for example, it would look real pretty going in, but within a day or two, it would be rusted like the Tin Man. So, it would be toxic inside the human body. But titanium, some of you may have titanium in your body, or know somebody who has titanium screws or wire or something like that from when they had an injury or an operation. 2 people in my family have titanium in them. My daughter has a titanium wire around her sternum. You can't see it, it's just a little wire that's in there. And my father has a titanium heart valve. And I have titanium in my prosthetic, but it's not in my body. One of the coolest metals in the transition metal zone is the only metal at room temperature that's a liquid, and that is mercury. Very dense. And I have a sample up at my desk, which if we have time, I will show you guys later. But I have to maintain a close watch on it. So we'll talk about that later. And it comes from the Latin. The symbol Hg comes from the Latin word for silver water. They used to give this to people as a medicine. They used to call it quicksilver. if you came to a physician in the Roman times, and with like an upset stomach or bowel problems, they'd give you this, like a whole cup of this, and you drink it. And, you know, sure, it might clean you out, but it would also kill you. So, little transition metal humor here. AU, get out of here. Get it? Gold. Okay. Part of the transition metals are the lanthanides and the actinides. Now, they are separated from the table simply to keep the table from being too wide. It wouldn't fit on a sheet of paper or neatly on a normal size poster like the one you see on the wall in the classroom. And elements in each row, they tend to have similar properties. The first one is the lanthanides. They're all metals, hence the term transition metals. They're all shiny, they're all reactive. Some of them are used to make steel, but all of them have uses in all different kinds of technologies. For monitor screens, computer monitors, europium, which is element 63, they used to use that. I'm not sure if they use it anymore on the modern day monitors, but these big box monitors from just not too long ago, 10 or 20 years ago, not even, they would coat the back of the screen with europium, and it would give that red color. Actinides is the bottom one. Actinides are all radioactive and unstable. And we know how radioactive elements change into other elements, atoms of other elements. So there's a question in your notes about that. Anything after plutonium, number 94, does not occur in nature. They're all made in laboratories. And you're familiar with this one because we've read an article about this, americium, element 95, used in smoke detectors. And it's found right there on the periodic table. Actinides. Because iron's symbol is Fe. Come on, people. Okay. Here's the second set of questions. I'm going to skip over this quickly, but you know that it is in your notes. And long story short, if these are disregarded, these questions, I'm not going to accept your notes at all. So make sure that you kick some butt on these questions, okay? All right, the boron group. Now we're on the right side of the periodic table, and we're going to talk about all these groups in succession. So the boron group has one metalloid, that's boron. Remember what a metalloid is. It has properties of both metals and nonmetals. And then 4 metals. And aluminum was that one metal that was the exception to the zigzag line, the staircase. Everything else that touches the zigzag line is a metalloid except for aluminum. Aluminum is a metal, very unique metal. This is a whole story about that. But you also have gallium, indium, and thallium here. But if aluminum is everywhere. I mean, aluminum is, they make aircraft out of aluminum. They make aluminum foil cans. The moldings around the whiteboard that this screen is hanging from are aluminum. But aluminum is flammable also. If I were to scrape some aluminum off and make a powder out of it, I could light it on fire and it would burn. It would turn into aluminum oxide, a white, grayish powder. And aluminum has a unique history itself. Aluminum is the most abundant metal in the Earth's crust. But for many years, we did not know how to extract it. It was a very expensive and painstaking process to get the aluminum out of the ground. So if, say, 100 or 150 years ago, if somebody was walking around with a aluminum snuff box or some aluminum case for something or whatever, they were very wealthy people because aluminum was more expensive than gold and more expensive than platinum back then. But now that we've learned how to get it out of the rock very easily, it's a very common metal and it's everywhere. But you can still collect aluminum and sell it at the scrap shop for money. It's still worth something. The next group is the carbon group. 2 metalloids, 1 non-metal, that's carbon. Carbon is a non-metal. And 2 metals, tin and lead. I have a whole slide about carbon, but silicone looks like a metal. It's not, obviously. And lead and tin are kind of similar because they both have low melting points. So remember that columns, they're called families because just like a human family, they have similar traits. But as you go through generations, grandparents, great-grandparents, grandparents, parents, children, and then grandchildren or whatever, the traits are similar but not exact, right? So it's the same thing here, and that's why they're called families. So the example that I wanted to tell you about this group was carbon itself. Carbon has natural forms this is what's special about carbon. And all those forms have different properties. So one of those forms is soot. And it's formed when you burn oil, coal, and wood. It's that black stuff that gets on your hands at a campfire or a barbecue. It's also the black stuff that's on your burnt toast in the morning that you scrape off because you left the toast in the toaster oven too long. It's used as a pigment in paints and crayons. Pretty cool. Graphite is those 2 middle pictures there, that shiny one and the pencils. Lead, but it's not lead. Pencils don't have lead in them. They haven't had lead in them for a very long time, hundreds of years actually, because lead is toxic. So they use graphite mixed. Graphite is a mix pencil lead is a mix of graphite and clay, and depending upon the percentage of graphite to clay, you get different colors or different darknesses, shades of pencil lead. That's why the number 2 pencil or number 3 pencil or number 1 pencil, or if you are into art, you know about these things and you know that there's a 0 and other levels, okay, of pencil lead that are used for art. And you could also use them for lubricating. It's very slippery stuff, graphite. I know that when my son, who's 22 now, when he was in the Cub Scouts, the only lubricant they were allowed to use on the wheels of their Pinewood Derby cars, the little cars that the Cub Scouts race, was graphite, because liquid or greasy ones would get on the track and make a mess. So the graphite didn't do that. And then finally, another natural form of carbon is diamonds. Diamonds, and these are shown raw and uncut. That's how you find a diamond in nature, like that. Are the hardest substance on the planet. Not meaning hardest, like if I hit that diamond right there with a hammer, it would break. It's not that kind of hardness. It's hardness that it can scratch anything else, but nothing else can scratch it. That's what hardest substance on the planet means, okay? And we've learned how to make industrial diamonds also. Diamonds, the only thing that will cut a diamond is another diamond. And as a side note, the only publicly accessible diamond mine in the world, I believe, is only a short drive away, maybe about a day's drive or less. It's easier to get to than, let's say, New York or something like that. In Murfreesboro, Arkansas. It's in southern Arkansas. And it's a state park. You can go and you can dig diamonds right there. For like $5. You just pay to enter the state park and you can camp there, and it's a really neat experience. Because it used to be an old volcano, and that's where diamonds are found, in old volcanoes, because they need a lot of heat and pressure to form. Okay, so the next group is the nitrogen group. I told you there's going to be a lot of stories about these elements, and this is just touching the tip of the iceberg. There are books written on all of these elements, volumes. As a matter of fact, the only book that I've ever read on any element, single element, is a book about phosphorus. And it's one of those books I told you that are extra credit for you. It's called The 13th Element. Even though phosphorus is the 15th element, it's the 13th element because it was the 13th element the name of the book is the 13th element because that was the 13th element to be discovered. Comes in different forms. That's red phosphorus there. Nitrogen, we know, makes up 78% of the atmosphere. It's a flammable gas, but you can't light the atmosphere on fire. Now pay attention to this. This is one of your questions on your quiz coming up. Because you can't get it hot enough. You would need a hot enough extended temperature for the nitrogen to chemically bond with the oxygen in the atmosphere and ignite the entire atmosphere, which would be very, very bad for life and for us. So yes, nitrogen combines with oxygen, but not as readily as you would think. Okay, so there's arsenic, which is famously used as a poison in many sad stories throughout history. Something called antimony, and then bismuth. And you've got two nonmetals, that's nitrogen and phosphorus here. And they're all solids at room temperature except for nitrogen, which obviously is a gas. The oxygen group is the next one. Oxygen, a top picture there is of liquid oxygen. Then you've got sulfur. I also have a sample of sulfur that I can hand out to you, you guys after these notes are over. And you can hold a real chunk of sulfur in your hand if you want to. Selenium, tellurium, and polonium. Polonium used to be put in a radioactive substance, was put in spark plugs for cars. That's crazy. They don't make them out of that anymore, but they used to. And if you look it up, you can find out why. We're not going to go into that one right now. But sulfur, I think, is the most interesting one. I mean, oxygen, obviously we need oxygen to breathe, and you learned all about that in biology. But sulfur is the only substance, the only element I know to do this. Years ago, I would do this in the classroom, but some people are allergic, I learned, to sulfur, and it's really smelly, so I don't do it anymore. But if you heat up a solid, what does it do? It melts, right? When you heat a solid, it melts and turns into a liquid. And guess what sulfur does? It does that. Ooh, okay, fine. Okay, what happens when you heat up a liquid? What does it turn into? Right, it turns into a gas, not sulfur. Sulfur, when you start at a solid, like you see there, and you heat it, it melts and turns into a liquid, very viscous, thick, molten sulfur. You may have seen some trucks driving around Central Florida that say molten sulfur on them. It's all about the fertilizer industry. Then you heat it some more, it turns back into a solid again. The crystals, the atoms rearrange themselves and form new crystals in a different shape, and it turns back into a solid again. And then if you continue to heat it again, it melts again into a later form of liquid. So that's weird. Imagine heating up ice. The ice melts, turns into liquid, and you heat the liquid more and it turns back into some weird form of frozen water again. How weird would that be? So sulfur is the only thing I know that does that. Pretty interesting. Halogens, we've talked a little bit about these in the last set of notes, so I'm not going to spend too much time on these. We know that they're very reactive. We know that they're used to kill organisms because that's why they put them in pools, and that's why Disney puts bromine in their rides, to kill bacteria and algae from growing in those bodies of man-made contained water. But you've got chlorine here. Chlorine, like I said before, 2 breaths, you're dead. But you take sodium, which we talked about before, sodium, a metal that when you throw it in water, it explodes like a grenade. Okay, deadly. You can't touch it with your hands. Just the sweat from your hand would make it burn and spark and pop in your hand. One piece of it, like the size of a pea or something like that. You take that and you mix, you chemically bond it to chlorine, which is a deadly gas, 2 breaths and your lungs stop working, right? You put them together, sodium and chlorine, and what do you get? Right, you get table salt, which you sprinkle on your French fries. I think that's a miracle right there. When you take 2 different elements and you chemically bond them together to make something that's got completely different properties, but the elements are still there. They still have the same number of protons and neutrons, okay? Their electrons are just bonded, which gives them different properties. It's almost like, you all know it. You all have a friend, or it might be you, who knows, but a friend who dates another friend. And originally, those 2 friends had their own lives and their own personalities, right? But then when they got together and spent time, were going out for a while, together they became this new entity, right? And they had different behaviors, okay? So that's a very good analogy when we're talking about how, and we're going to talk more about this in the next unit. And then this is the final chunk of questions that are all in your notes, your guided notes for a grade, okay? So make sure that you spend some time on these. They're not due tonight. Don't worry. They're going to be due a couple nights from now, probably, okay? But definitely before the test. So, and then the final one, the final family that we're going to talk about is the noble gases. We are familiar with the noble gases and their fact that they have a full outer energy level. Okay, so there's a question about that in your notes. And we also wrote an essay about neon lights, so you're familiar with how those work and that different gases, when energized, make different wavelengths of light. They're not chemical reactions, they're just electrons quantumly leaping, right? Remember that? But the one I want to talk to you about is the bottom one, radon gas. Radon is a naturally occurring radioactive gas that comes from the breakdown of the Earth's rocks inside the crust. And it occurs naturally through radioactive decay inside the Earth. But then normally the radon gas would just leave the Earth and go up into the air and not be a problem for anyone. The problem is when people build houses. Not so much here in Florida because there aren't many basements in Florida, but when people have basements, they tend to be kind of airtight. And so the radon gas slips through the tiny cracks of the cement and it builds up in the air of the basement. So if you spend a lot of time in a finished basement that's inside the earth, you could get a toxic dose of radioactive radon gas. So they sell these things called radon detectors, which if radon gas is detected, they turn on a fan, which totally exchanges the air in the basement and makes it safe. This is a perfect pun for noble gases. And I bet you feel like that cat right now. Okay, so we didn't talk about hydrogen because hydrogen is a little special, unique element. It's put on top of the alkali metals, so the very first column. And the only reason it's there is because it has one valence electron, okay? But we know it's not a metal, obviously, right? And it's still very reactive, just like all those metals. Now, it won't react with water, but it will react with oxygen. If you give it, remember the fire triangle from the very first week of school? You add oxygen and heat, and hydrogen's the fuel, and kaboom, you have an explosion. Like the Hindenburg in 1937, the Hindenburg disaster, a spark caught the aluminum skin on the outside of the Zeppelin to ignite the hydrogen inside, and caught the whole thing on fire. Now, see those guys running underneath right here? These are sailors in the Navy who were getting the lines that were being dropped from this airship back in 1937 to dock it in, I think this was in New Jersey, I'm not sure, anywhere, somewhere up there. But when it started to fall, they all started to run. Well, I knew one of these guys running down here. I knew him when he was an old man in the 1980s. And he was kind of like an uncle to us, me and my cousins, because he was also a firefighter. And there's actually video of this happening if you go on YouTube. So that's what that link is there. All right, we're going to switch gears a little bit here, and we're going to talk about trends in the periodic table. So I hope you have your periodic tables out because you were asked to have them out all the time or at the ready, and you're going to have to draw some arrows on your table. So if you feel rushed, come back and do this later, okay? So there are 4 trends we're going to talk about. The first one is atomic radius. And you can see that the bottom left of the periodic table, the radius is greater than the top right. So you can pretty much draw an arrow from, and I'm going to show you the arrow to draw in a moment, so don't do it just yet, but from left to right. It has to do with electron configuration. So the electron configuration makes the atoms bigger or smaller. Even though these atoms over here have more neutrons and protons and electrons, they're not as big as these over here that have less. And so pretty much as you as you move from left to right, the atomic radii decrease. And as you go down a group, the atomic radii increase. So as you're going down the boron group, the atomic radii is getting larger and larger, okay? As an example. So here's the trend. So you're going to draw these arrows and label them. You have to draw some more arrows, so don't draw them too large. I would draw just a single line and then label it. Maybe you can color coordinate it or something. That's why you should take time and do this where you can think about it. Because you're going to need to know this on your assessment for this unit coming up, as well as on the final exam, semester exam. So we're going to move on to the next one. Ionic radius. Ionic radius. So this has to do with ions. So the electrons have changed number. You've lost or gained electrons. And they've become positive or negative. Well, when that happens, you're going to change the radius of the atom because you're adding or reducing the number of energy levels. If you add an energy level, a negative ion, because you're getting more electrons, it's going to get larger, okay? So generally, left side atoms form smaller positive because you're losing electrons, and right side atoms form larger negative because you're gaining electrons, okay? And this is an example really quick. So you've got lithium becomes positive, so it loses size. It loses an electron, it loses an energy level, it gets smaller. Whereas fluorine becomes negative when it becomes an ion. It gains electrons. So it gains an electron, so it's going to gain an energy level, so it becomes bigger. Okay? Gaining electrons bigger, losing electrons smaller. And here are the arrows that you should draw on your periodic table without disturbing any other information. So I know it's a little tricky, but there are several different orientations of arrows that you need to include and label for ionic radius. So we can remember, we're not going to spend class time doing this. You can you should come back and do this in a more organized fashion. I'm just going over the idea right now with you. The next one is ionization energy. So this is the energy it takes to remove an electron from a gaseous form of the atom, okay? And simply put, from left to right, this energy generally increases, and from top down, it generally decreases. From the bottom to from the top to the bottom. Ionization energy. And then I think the last one is electronegativity. So the electronegativity of an element indicates the relative ability of atoms to attract electrons in a chemical bond. And we're going to talk more about this later, but the electronegativity it determines its reactivity, okay? So if its ability to attract electrons is better, then it's going to be more reactive. Does that make sense? Okay. And you can see by this little 3D model that pretty much mostly that as you go from left to right on the periodic table, the electronegativity increases. And here's the arrows for that. Electronegativity increases from left to right and from bottom up. And the generalization of both of those arrows are that center one going through the middle, but you probably don't want to draw right down through the middle of your periodic table. So the outside arrows are best. And then this is all of them together in one great big arrow-filled periodic table. But you obviously don't have one that's oriented this way, so your arrows are going to be a lot smaller. But still color coordinate them like this, and it will be very helpful in the future. Okay? So let me show you the mercury and sulfur now.